Okay, so this class is basically a problem solving class, and the idea, the concept that is required for this particular problem, uh, that is basically divided into different units in your syllabus. For example, in unit number 2, you have studied about the bias calculation of a BJT, right? And in unit number 3, you have studied the small signal characteristics in the midband region. And then in the next year, in unit number 4, you have studied about the frequency response characteristics, right? Now, in order to find out the frequency response behavior of any amplifier circuit, let it be a common emitter or common base, you need to know first of all, you need to know how to bias the circuit, what are the different components that are required, and then how to put the midband gain. That is quite easy, relatively easy. Then comes the frequency response behavior in the low frequency side and the higher frequency side. Hopefully you can remember that the low frequency response is basically governed by the external capacitors like the coupling capacitors, bypass, right? And the high frequency operations in the range of say a few hundreds of kilohertz or beyond kilohertz, right, in the range of megahertz, that is basically governed by the internal capacitors, right? So one side you have, so whenever you observe this low frequency operation, that means this entire circuit behaves like a high pass filter. On the other hand, whenever you observe the high frequency response, that means the circuit behaves like a low pass filter, right? And apart from that, apart from the calculation, the additional thing is that I'll also demonstrate how to use a semi-log graph paper, because ultimately whenever you are asked to draw the these frequency response characteristics, in that case, if you are very much accurate, then obviously you cannot write. I mean, you cannot draw it on either on a plain paper or on a linear graph paper, for which the semi-log graph paper is required. Why semi-log? Because I have told you last day that here we are interested in observing the variation from say few tens of hertz to few hundreds of megahertz, right? So linear graph paper means you understand that tens of hertz, or 10 hertz or 20 hertz, and go up to say 100 megahertz or 200 megahertz, right? So 2 to the 200 means how much? 200 10 to the power 6. So something like 10 hertz or 20 hertz to 10 to the power 6, it is not possible to draw on a linear graph paper, right? Even if the graph paper is provided, then the size of the graph paper just imagine, right? So in that case, obviously you have to go for a semi-log graph paper. Now before I go there, let me just explain the mathematical part, the explanations, these mathematical calculations, and then so basically we have the two different components of this discussion. First part is the mathematical calculation, and second part is the plot of this particular graph, right? And accordingly, we have two different slides. We have two different PDF over there. So first one is basically the calculation part, right? So as you understand, this is nothing but a common emitter amplifier. Common emitter amplifier with the different capacitors are present. Like you have the coupling capacitor, the value is 1 microfarad. Last we have explained why this is in the range of microfarad, not in the picofarad or nanofarad. Then you have this bypass capacitor, this like 10 microfarad there. We have a load capacitor as well, 10 microfarad. And we have these bias resistors like 47K, 12K, this pair, voltage divider bias. Apart from that, you have this emitter resistance 1 kilo ohms, and you have this collector resistance 3.3 kilo ohms, and you have this load resistance 10 kilo ohms. That is the circuit, and you understand it's basically a common emitter amplifier circuit. Common emitter amplifier with common emitter amplifier with emitter bypass capacitor, right? And apart from that, you have some properties which have already been mentioned. The properties of the transistor, beta DC is equal to 75, beta AC is equal to 70, C pi, that means the base emitter capacitor, that is equal to 20 picofarad, C mu is equal to 2.4 picofarad, and fortunately, thankfully, V equal to infinite. That's great, because if V equal to infinite, that means R naught, that is equal to infinite. That means in your calculation, you don't require any R naught, right? That is a good thing from your side. Anyway, so to start with, first of all, you have to perform the DC analysis. So for DC analysis, we have to go for, in finding out the Thevenin equivalent, what is that? Basically R1 R2 parallel combination, right? 47K, 12K, if you calculate, you'll be getting like 9.6K. That's very easy. and the Vthevenin is nothing but this 12 divided by this, the summation of these to 47 plus 12, right? And then ultimately multiplied with, okay, the Vthevenin value is equal to 12 by 47 plus 12 multiplied with the VCC, which is equal to 18 volt, and accordingly you are getting this Vthevenin to be 3.66 volts. So ultimately the circuit, this base emitter circuit reduces to this one. You have this Thevenin equivalent voltage Vthevenin, and you have this Rthevenin, and you have this particular resistance in the form of Re, right? And beta DC is given. Beta DC is in the form of say 75, and accordingly if you apply this case KVL in this particular loop, then this voltage equal to this drop plus VB drop plus the drop across the emitter resistor, right? So accordingly you have this 3.66 is equal to 9.6 in IBQ, that means I is represented in the form of milliamperes. So that's why I can simply write like 9.6 in IBQ, because 9.6 is in the range of kilo ohms and IBQ is in the milli. And then you have this 0.7 drop. Although it is not provided, but you can safely assume that it is 0.7 volt. Then 1 plus beta times IBQ, that is IEQ times RD. What is IEQ? 1 plus beta times IBQ. So 1 plus beta times IBQ, and IB is in the milliampere, multiplied with 1 kilo ohms. So accordingly you can get IBQ is equal to 34 microampere and ICQ is equal to 2.55 milliampere, and R pi, you know the formula, R pi BT upon IBQ, and accordingly you will be getting the R pi and GM. So once you get this, that means your DC calculation is over, right? Your DC calculation is over. Now you have to do small signal analysis and in the midband region. Now whenever you are in the midband region, then you can simply just neglect the effect of the capacitors. You can simply neglect the effect of the capacitors. What are there? So although it is not mentioned, but here I am assuming that this input signal source is having a signal source resistance of 50 ohms only, right? Input signal is having a source resistance of 50 ohms. So accordingly, so now we find that this is your base terminal. This is the
50 ohms is RS.
RS, signal source resistance RS. If it is not given, you just consider it to 50 ohms, right? So this is your base terminal. This is the collector terminal. This is emitter terminal. And in the small signal equivalent circuit, right? Whenever you find any capacitor in the series path, you assume that in the midband region, you assume that this capacitor is acting as a short circuited path. And whenever it is in the shunt path, parallel path, you consider the capacitor is acting like an open circuit, right? I mean, so in that particular case, what I find, so what I get, okay. So you find that, okay, this 1 microfarad and 10 microfarad, these two capacitors are there. 1 microfarad is your coupling capacitor and your 10 microfarad is your bypass capacitor. So these two capacitors are present, and then what I get, I am assuming that at the midband region, midband means what? That means in the range of tens of kilohertz, in that particular range, tens of kilohertz or hundreds of kilohertz over there. So over there, the coupling capacitor will provide a very small value of your impedance. So I can consider that this coupling capacitor is basically acting as a short circuited path. Okay. That is acting as short circuited path. So from here to here, here to here, you actually have a capacitor over there. You have a capacitor present over there, the coupling capacitor. But I am assuming that at my signal frequency in the range of kilohertz or hundreds of kilohertz, in the midband region, this coupling capacitor is basically acting as a short circuited path, right? And if you just once again consider what is the value of your bypass capacitor, that is in the range of 10 microfarad. So once again, this bypass capacitor, just consider from emitter to ground, you have basically you have two different elements between emitter and ground. What are those? One is your this resistance, 1K resistance is there, and apart from that you have this 10 microfarad, right? So 1K resistor, that particular thing is insensitive to frequency. So actually it will provide you some impedance. But when it is coming in parallel with the 10 microfarad and the signal frequency of 100 kilohertz or so, this 10 microfarad is acting as a short circuited path, right? So this is actually short circuit. This is short circuited path. This one, right? Because 1 micro, 10 micro, they are in the short circuited path. Once again, obviously, apart from that, you have some internal capacity, if you can remember. So one was there between base and emitter. You have one internal capacitor, right? And you have one internal capacitor between base and collector. But with the signal frequency of 100 kilohertz or 10 kilohertz, I am assuming that these capacitors are providing very high impedance, right? Because it is in the range of picofarad, not like your CC or CE. CC and C is in the range of microfarad, and these capacitors are in the range of picofarad, right? So what about your impedance? You know the impedance is given by 1 upon SC. So as C is less, your impedance is more. So here C is less, pico. These capacitors like C pi and C mu is in the range of picofarad. C is less, So therefore the impedance is large. So if the impedance is large and they are connected in this manner, so you can just neglect them at mid-band region. Okay. So then the circuit is relatively easy, and then ultimately you are left with this one. You have this one, this 9.6K in the form of R Thevenin, and this 9.8K is nothing but your R pi. You have this 9.6K in the form of R Thevenin. You have this 50 ohm signal source resistance, and then obviously you have this GMP pi, voltage dependent current source. Thankfully R0 is not there. R0 is absent because V equal to infinite, and you have this 10K resistance. What is that 10K? 10K is basically your load resistance 10K, and once again you have this capacitor. This capacitor is there, load capacitor is present, but once again I can assume that at signal frequencies load capacitor is basically acting as a short circuit, right? So from here to ground you have this 10K, from here to AC ground you have another 3.3K, RC and RL. Okay, so you have 10K, 3.3K. So now the circuit is relatively easy. Now, okay, you have these two capacitors in parallel, this one and this one, these two capacitors are there in parallel, these two resistors are there in parallel, this 9.6K, 9.8K, and you can find out this equivalent resistance, that is 4.85K, this one. And once again, you have this 10K and 3.3K, these two capacitors are there. You can find out the effective capacitor like 2.48K, and the circuit is something like that. It's relatively easy. You know that this is my Vin, the applied voltage. You have some coupling loss present over there because of this 50 ohms resistance. You have this 4.85K, so most of the voltage will be developed, will be coupled at the input. You have some coupling loss. What is that coupling loss? You can simply calculate this one. What is that? 4.85 divided by 4.9. The total resistance is 50 ohms. That means how much? You can calculate, that is 0.005 kilo ohms, right? So 4.85 plus 0.005, 0.05 rather. So 4.9 and 4.85, so it is 0.99 of Vin. So 99% of the signal is getting coupled at the input of your transistor, right? And this is your GM Vpi. This voltage is basically the Vpi voltage, and you already have got the relation between Vpi and Vin. Vpi is equal to 0.99 Vin, okay? And your what is your V0? V0 is nothing but minus GM Vpi times this resistance, 2.48K. If you just plug in those values, and then ultimately V0 upon Vin is coming out to be minus 17.19. That is the gain of the amplifier in the mid-band region. That means it will give you a gain of close to 18 or so, or 17. Right? So up to this, it is little easy, and you have already we have done this exercise many times before.
Sir, in the mid-band region, you said that the impedance of C and CMU are removed the reason.
Okay, so what we have, you have these two capacitors are there, basically C pi and CMU. This C pi is there between these two terminals, and CMU is there between base and collector. This is C pi basically, and this one is CMU, right? Now mid-band means I am assuming that my signal frequency, say let it be 100 kilohertz. Let's consider this is my signal frequency, 100 kilohertz. Not very small, not very large. Neither very small, not very large. 100 kilohertz. Okay, so 100 kilohertz. Now this is your F. This is your F value. F is equal to, and what is your X of C? That is, as you know, that is 1 upon J twice pi F times C. Okay. Now if you just simply plug in those values, now consider that C is equal to say for example it was like how much? What was the value?
20
pi 24.
24 PF.
24 PF, yeah. So if it is 24 PF, so let it be 24 PF. So let's consider 24 PF. And then is the picofarad. So picofarad is important, 10 to the minus 12, right? So 10 to the minus 12 multiplied with C, your F is in the range of 10 to the 100 kilohertz, that means 10 to the power 5. 10 to the power minus 12 multiplied 10 to the power 5. That means in the denominator you have in the range of 10 to the power minus 7, right? So if it is 1 upon 10 to the minus 7, so that means 10 to the power 7 by something, right? So that is relatively large. So you can simply get rid of this particular capacitor, like this C pi and C. What about your CC and CE and CL? For them, you know that capacitor is basically in the range of, so this is basically for C pi. And for CC or CL or CE, typically they are in the range of microfarad. Let it be 1 micro, 10 micro, and then microfarad. That means 10 to the power minus of 6. Right, 10 to the minus of 6. Okay. And what you have, F is 100 kilohertz. That means 10 to the power 5. 10 to the power 5, 10 to the minus 6. So comparable and almost 1 upon 10 or something. 1 upon 10 to the minus 1. So ultimately your this particular impedance X of C is equal to like few ohms. This much only. So that's why you can now neglect in the series part. So this XC for this CC or CL or CE is in the range of say tens of ohms, in the range of tens of ohms, right? So you can simply neglect because it is in the series path. You can consider okay they are short circuited, but the same value X of C for your C pi and C mu they are in the range of how much 10 to the power minus 7 I called, so in the range of megohms. So that's why you can simply neglect because that. So if it is there, some megohms is there. This is there over between this base to collector in the shunt path. So you can consider okay. So that particular capacitor is providing very high impedance. So okay, it's almost a short circuit. Okay. Okay. So far so good. So now comes the. I mean, up to this it is easy. There is no capacitor. Now the tricky part is coming. Now we are observing a low frequency region, and the low frequency region now if the frequency operation is even less, as of now we have considered 100 kilohertz, right? Now even less in the range of say tens of hertz or hundreds of hertz, then obviously okay you can get rid of the C pi and C mu, that you can get rid of because that impedance is even more, right? Because it is 1 upon twice by FC. F is reducing, so obviously that impedance is even more, so you can just forget about the C pi and C mu. But what about your these capacitors, the CC and your CL and C, that you cannot neglect right now because now the frequency is less. Now if the frequency is less, so obviously and these capacitors are in the range of microfarad, so now you have to take into account those capacitors, right? So obviously now in that case you have to draw this input RC circuit. How does it look like? So what I get? So everything is the same. The only difference is that now you are incorporating this 1 microfarad, this capacitor, and you have incorporated this 10 microfarad, these two capacitors. In the input side, you have incorporated this coupling capacitor, and over here this bypass capacitor. So as of now, in the mid-band range, you have just considered that okay, this terminal is connected to AC ground, right? Because this particular capacitor is providing you a zero impedance. But now it is not true. Now it is not true. So obviously you have this capacitor present, and accordingly, now if you calculate this V pi upon V in upon V pi upon V in, now obviously that particular thing is now a function of frequency. It is no longer independent of frequency. As of now, you have seen like V pi upon V in is equal to 0.99. It's not a function of frequency in the mid-band region. It's constant. But now if you calculate this one for this, because now we have this capacitors are there. At least two capacitors are there. This capacitor CC, this capacitor CE. So these two capacitors are there, and now this V pi upon V pi upon V in, that will become a function of S, right? And accordingly, it's a function of frequency. So we have to do that. So worry about actually the calculation is little bit tedious.
Sir, এখানে ওই GMP by যে কারেন্ট সোর্স দেওয়া আছে এর ছিল ওটা ঠিক আছে?
And that is there in the output side, collector to emitter. We would like to find out what is the amount of signal that is getting coupled at the input, right? Over here. GM pi is there in that side. You have GM pi that side, right?
It's a short circuit.
No, it is there, but I have not drawn. That is not required for this timing. That is obviously there. You have this GM pi. You have this GM pi. You have this RO parallel. RC parallel RL. So all the parts are there, but we are interested in finding out what is the amount of this V in that is getting coupled over V pi. What is the V pi upon V in? Because this V pi to this RO, V pi to VO, that particular thing is no longer a function of frequency. Because what you have over there, this output voltage, how much? GM V pi times RC parallel RL minus 10 outside. It's not a function of frequency, right? You have these capacitors. Okay, you have two capacitors, and you have got rid of those two capacitors. Okay, so now the frequency dependent part is there over here from V in to V pi, that relation V in to V pi. V pi to VO, it is not, it's no longer a function of frequency.
So what about the capacitor which was there in the collector to output?
Collector to
output, there was a capacitor in between.
Yeah, that means another coupling about load capacitor talking about, right? And that we will observe in the output side only. That is input RC circuit. We will observe this in the output while analyzing the output RC circuit. Okay, so fine. So now what you have? You have now you have 1K 10 micro parallel. These two are in parallel. This is an impedance. What is that impedance? You can simply calculate R upon 1 plus SRC. You have one capacitor. You have already studied in your circuit theory course. You have this resistance R and you have this capacitor C. They are in parallel. what will be the equivalent impedance? This is nothing but R by 1 plus SRC. Right? So it is coming out to be 1000 by 1 plus 0.01 S. Right? That is your Z1. And this Z1, this is Z1. Basically, we are calling this is as Z1. This is Z1, and this Z1 is coming in series with this 9.8K. Right? In series. So I can call it a new impedance. Let it be Z2. That is 9.8K plus Z1. That is 10,800 plus 98S upon 1 plus 0.01S. Very simple calculation.
Yes.
Right? And then this one is coming, and then this entire thing is coming in parallel with this another 9.6K over there. Right? So let me call this as Z3, this impedance. That is coming out to be this much, 9600 multiplied with this one divided by this one. Okay? Now you observe this part of the circuit. Okay, so yeah. So
in series with that.
So then what we have over there, suppose this current is I in, this current is I in, and this current is I1, say for example. Okay, this current is I in, this current is I1. So first of all, you have to identify what is the amount of current, and this current is I2. This is I1, this one is I2. So if you simply apply KCL at this particular node, at the base node, so I in is equal to I1 plus I2. Right? And what is your V pi? V pi is nothing but I2 times R pi. V pi is nothing but I2 times R pi. R pi you have already calculated 9.8K multiplied with this I2. That will give you V pi. Right? So now we have to find out the relationship between this I1, I2 and I in. I know that I in is equal to I1 plus I2, and how is it related to V in? That means V in versus I2. I'd like to find out. And then from I2 to V pi. I2 to V pi is equal to, V pi is equal to I2 into 9.8. That's it. So now we would like to find out what is your what is the relation between V in and your I2. Okay. So what will be your V in? How I in is related with V in? How is it related? What is the formula? You have to find out. Okay, already up to this you have calculated this. Up to this you have calculated what is the impedance. This part you have calculated. What is that called? Z3. That is called Z3. So you have Z3, you have 50 ohms, and you have this 10 microfarad, 1 microfarad coupling capacitor. So they are in series, right? So what will be the effective? What will be the current I in? This V in upon this entire thing. V in upon 50 plus 10 to the power 6 upon S plus Z3. Just substitute those values. Right? What you get? This much. You'll be getting this much. This is your I in S as a function of frequency. Right? And then what is the relation between I in and I2? How are they related, I in and I2?
Division.
Right.
Z2 by 9.6K divided by 9.6K
plus Z2. Right. So I2S is equal to I in S divided by 9.6K plus Z2 multiplied with your 9.6K. Simple voltage division law, as you know. Right? Okay. And that's already known that your V pi S is equal to I2 times 9.8K. And then if you just plug in all those values, I appreciate that this calculation is relatively tedious. It will require enormous amount of time. It's a tedious calculation. Anyway, if you do this calculation, then ultimately what I get over there is this much. V pi upon V in. V pi upon V in. V pi is there. V pi is equal to V in S upon this. This is basically your I in S. I in S divided by your this one 9.6 plus Z2 multiplied with this 9.6 multiplied with this your 9.8. And if you just do this calculation, then ultimately what you are getting, you have two capacitors in your circuit. Two capacitors, one the coupling, second one is your bypass. Two capacitors, ultimately it will give you a second order system, and that is so ultimately what you are looking at. This one, this is the expression. What I get, what I am getting, right? 0.9408 S multiplied with 1 plus 0.01 S divided by 204 plus 2.987 S plus 0.0095 S square. That is the relation between V pi and V in. Last time what we have got? Last time you have seen that value is equal to 0.99. It's not a function of, it's no longer a function of your frequency. Right? But this time it's a function of frequency, and it is something like that, 9.9408 is, and so on and so forth. Okay. So coming at this point is a challenging. Right. Starting from this and by calculating, I mean by writing the expressions for KCL and KVL and all these things, then ultimately you have reached at this point. Once you have reached at this point, that means your half work is done. 50% work is done at least. That means V pi upon V in 0.9408 is multiplied that much and this much. Okay. 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 Now, what is your voltage gain? Voltage gain is nothing but VO upon V in. So VO upon V in is nothing but VO upon V pi into V pi upon V in. Okay. Now, what is your V pi upon V in? Already you have calculated V pi S by V in S. Now you have to replace this S by J. Last day I told you that S should be replaced by J times this capital omega. That means J times twice pi F, and F is your angular frequency. F is your Hertz frequency. Capital omega is the angular frequency, and ultimately you have to plot it with respect to your Hertz frequency. Right. S is equal to J omega, that is J into twice pi F, and F is your Hertz frequency. You have to plot it with respect to this Hertz, megahertz, with respect to this F. Okay. So then what I get this much. It's a calculation. It's a calculation. I'll provide it to you. It's not a big deal. You have to just check whether you're getting this one or not. Anyway. Okay, fine. So 0.9408 into S. S is how much? J twice by F. Now the complex number calculation. I don't know. I mean, I think that you have done it in your class 12 level. Higher secondary level, you have done this. Class 12, no? This complex number and all these things. Class 11, class 12. Now once again, our encyclopedia. This one. 0.9408 and then this J twice by F. Okay? And 1 plus 0.01 S. 1 plus 0.01 J twice by F. Okay? That means the numerator part, the denominator part, you have this A plus IB by C plus IB. Right? Thankfully, I'm not. You are not asked to draw the phase angle, only the amplitude, only the gain part, not the phase angle. Thankfully for you. That I've told you, na. Anyway, so ultimately what you are getting is this one minus this much minus 0.3714 f square plus j into 5.91 f divided by this thing. So this is the real part. This is the imaginary part, A plus IB or A plus JB divided by C plus JD, like this. Right? Once you do this, that means your work is 70% done. Okay? Now comes, now almost towards the end of at least this low frequency operation. So now you just plug in the values. F is equal to, let's take F is equal to 10 Hertz. F is equal to 10 Hertz. You are getting the value 0.278. F is equal to 50 Hertz, 0.818, the modulus, magnitude only. 100 Hertz, 0.94, and 1 kilohertz, 0.986. So as you are increasing the frequency from 10 to 50, 50 to 100, 100 to 1000, as you observe, your gain is increasing, the mod is increasing, right? 0.278, 0.818, and then 0.94, and then 0.986.
So,
it is better to take this 10, then 100, then 1K like this, right? 10, 100, 1K like this. So, okay, and ultimately at 10 kilohertz it is 0.9. So it gets saturated after 1K, right? After 1K saturated. So ultimately what you are getting over there, freehand if I draw, frequency versus gain. So it's basically, it is like this, right? Initially increasing, and then ultimately beyond 1 kilohertz, it gets saturated. 0.986, 0.986. Now once you get this saturation value, you must stop your calculation. It's a high pass response. It's a high pass response. As frequency increases, the gain also increases. 1 kilohertz, 0.986, 10 kilohertz, 0.986. Done? Any doubt up to this? The calculation is tedious, I must appreciate. The calculation is tedious, but it's very straightforward. Okay. Anyway, so now we move to the high frequency. Now the second part is there, high frequency region. So high frequency region, obviously you have to get rid of your coupling capacitor and bypass capacitor, right? So what you have, you need to have the internal capacitors in the form of C pi and in the form of C mu. So C pi, you know, C pi is there as a C pi because it's a common emitter amplifier. C pi will be there between base to emitter, right? And in the high frequency region, this is basically connected to AC ground. Why? Because here at the high frequency operation, this bypass capacitor and as well as the coupling capacitor, they are providing you a zero, almost a zero impedance. Very small, low impedance, so you can just neglect this one. So it is connected to ground. So you have this capacitor 20 picofarad. 20 picofarad is there between base to emitter, C pi, and you have to consider the Miller effect. Miller effect you have to consider 1 minus A times C mu. 1 minus, because I am decomposing the C mu capacitor between the input and the output terminal, right? Right. So 1 minus A times A is minus 17.19 and C mu is your 2.4 picofarad. Okay. Any doubt? Which one?
Sir, oil capacitor है value
it was actually what was given C pi was given as 20 picofarad at the very beginning of your problem, and C mu was given as 2.4 picofarad. 2.4 pico. These are given. So between base to emitter you have the C pi 20 picofarad, and between base to collector you have C mu, and we have decomposed this C mu as C mu 1 minus A times C mu between base and ground, and between collector and ground you have. Can you remember this one? What is that? The decomposed capacitor between collector and emitter, collector and ground, collector and emitter. What is that? It's almost close to C. Almost close to C for a common emitter amplifier. So therefore, what I get, there is a Miller magnification at the input side, 1 minus A times C mu, and you have to consider the gain, considering the magnitude also, considering the space, the sign also. 1 minus A, what is your A? A is minus 17.19. So ultimately it is coming out to be 43.66 picofarad. Right? Now we have already discussed this one. That what we have discussed in our, in one of the lectures we have discussed. That we have discussed. So now we have two capacitors in parallel. You have two capacitors in parallel. So what is the equivalent capacitors? It's basically the summation. 63.66, and you have this 4.85K over there and this 50 ohms. Then how does the circuit look like? It's a low pass filter. It's a low pass. Right. R and C is there. It's a low pass. And accordingly, so if you can remember in our class what I have told you, and whenever you find this kind of thing, then you have to find out what is your RS, RP. What is RS? 50 ohms. What is RP? 4.85K. What is your C? That is 63.66 picofarad. And from that, you can calculate the effective or the approximate value of your corner frequency. What was that? We have mentioned, okay, F is equal to 1 by twice by tau. What is your tau? Can you remember this one? RC. That means your RS, RP by RS plus RP for this kind of circuit multiplied with this, okay, let it be CP. Okay. So that's an approximate calculation that we have done. RS, RP, RS plus RP multiplied with CP. Right? But this time we will not do that because we have to go for this extensive calculation in the high frequency range as well. Right? So therefore, once I get this circuit, once I get this particular circuit, this one, then I have to once again apply this KCL and KVL, and I have to find out the relation between this V in and V pi. The same thing that we have done for your low frequency region. Okay. So what is that? Once again, this 4.85, 63.66 picofarad parallel. You find out this capacity. The impedance. It is coming out to be this much. 4850 upon this one. 1 plus 0.308 into 6s. That is Z equivalent impedance, right? What else? V pi. So what is the relation between V pi and V in? What is the relation between V pi and V in? This one is basically your Z. Yeah, this one is Z. This is 50 ohms. So what is the relation? Z by Z plus 50. Z by Z plus 50, and then what you get is this much. 4850 upon this. I am interested in finding out this one. This is the expression V pi by V in, V pi by V in, and V pi f by V in f. If you just simply, now thankfully it's a first order. It's a first order RC circuit, and ultimately 4850 upon 4900 plus J to this 96.7 10 to the minus 6 f. That's it. then what we are doing? Then now so last time we have stopped at 10 kilohertz. Last time I stopped at 10 kilohertz. Remember the value was 0.986. 0.986. Now for this circuit, with V pi f by V in f is equal to 4850 upon this much. Now if you just find out the value of this gain, modulus of this gain at 100 kilohertz, it is coming out to be 0.989. So up to 2 decimal point, it is 0.98 only. Up to 2 decimal point, it was 0.986 there, and here it is 0.989. It's almost constant, right? At 1 megahertz, you understand that f is there in the denominator. So as we increase frequency, the gain will drop, right? So then, at 1 megahertz, it is coming out to be okay. At 1 megahertz also, it is constant at 0.989. At 10 megahertz, it is coming out to be 0.97, little bit less, 10 megahertz, okay? And then, if you move further at 100 megahertz, it is coming out to 0.447, significant drop, 100 megahertz. 0.447, and at 200 megahertz, it is 0.243. 0.240. Now it is 0.240, so you can stop it over there. No need to go to say 1000 megahertz, not needed. 1 gigahertz, not needed at all. Either you go for 200 megahertz or 500 megahertz, doesn't matter, because ultimately you have to find out the bandwidth. Now, whenever it is like 0.243, so you understand that from 0.989 to 0.243, so 70% we consider that half power bandwidth. So this half power bandwidth they have already achieved. So no need further. At 200 megahertz you can stop. So what we have done? So we have found out the gain expression, the gain value at 10 hertz. At 10 hertz the value was 0.27H. At 50 hertz it was 0.81H. At 100 hertz it was 0.94. At 1 kilohertz it was 0.986. 10 kilohertz 0.986. And then at 100 kilohertz 0.989. At 1 megahertz 0.989. At 10 megahertz 0.97. At 100 megahertz it is 0.447. At 200 megahertz it is 0.243. Now ultimately we will exploit these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values. We will exploit these 10 values to plot the frequency response characteristics of this common emitter amplifier, incorporating all these different elements. Still, one part is left. What we have done so far, we have only utilized the input RC circuit. As Harshad has mentioned that okay, there is some output RC circuit as well, right? So once again, if you consider this one, for the output RC circuit, you have got ultimately this much. But remember, I have mentioned many times during our discussion, theoretical discussion, that eventually this bandwidth is governed. This bandwidth is governed by the input RC circuit. Why? I have also mentioned. So that's why, thankfully, you can simply show the diagram. How does it look like the output side? But this output RC circuit will not govern the bandwidth. This bandwidth is essentially governed by the input RC circuit. So with input RC circuit, you can do all these calculations and you can plot the graph. It's not needed. It's not needed. Okay. The gain is 17.19 at midband. This, remember that 0.9, what I have told over there, that's 0.989 and all these things. This is basically the ratio between V pi and V in. Right? V pi by V in. That is the relation. But actually, this gain, we are interested in finding out what? V naught by V in. But remember that V naught by V pi, that is always constant, 17.19. So 17.19 multiplied with this. So I can consider that, okay. So we are interested in finding out V naught F by V in, this output by input mod. Right, so this is basically mod of VO by V pi multiplied with V pi by V in. V pi by V in. Now, as of now, what we have done, we have emphasized our analysis on this V pi by V in. Right, this is always constant, V naught by Vf, 17.19 multiplied with this much, V pi by V in. How does the signal get from the input to the input of the transistor? From the input signal source to the input of the transistor, how does it couple? So accordingly, we found out that okay, this value is not constant, V naught by V pi by V in. However, this V naught by V pi is always constant, this much, V pi by V naught by V pi, because as you understand this, what is your V naught? V naught is nothing but Gm V pi times minus Gm V pi times RC parallel RL. Right, so there is no, frequency dependent terms. Only you have this Gm V pi times RC parallel RL. Okay, but this V naught by V, but this your V pi upon V, that is very much a frequency dependent parameter, and accordingly there is a variation.
Oh, the node is 70.19 over J1 circuit.
17.19 multiplied with this. Overall gain, if I consider, as I have told you, this 0.278 or 0.818 or 0.94, this is a fraction. This is the second, this fraction. This is this fraction, V pi by V, this fraction. Okay, this is this fraction. So at, say for example, at 100 hertz, we have got that this value is equal to 0.94. 0.94. So what is overall gain? 0.94 multiplied with 17.1.
17.19. All किससे की होते हैं voltage
that is the mid-band gain. That's the mid-band gain. But overall gain, if I consider V naught by V in, this is basically the product of two. V naught by V pi multiplied with V pi by V in. As you observe that V naught by V pi, what is there? You have this part. That is your output. So this is GM V pi, and this is your say RC parallel RL. Right? So this V naught, so if I call this is V naught or V naught F, so this V naught F upon V in F, or rather V naught F by V pi F over there. So that is becoming always your 70.19. But the overall gain is how much? V naught by V in. That gets, that is different. That gets altered because of this frequency dependence part V pi upon V in. That is not constant. Okay. Anyway, so this calculation part is over. Now, what we do now, we will move to the next part. That means the, this part is over. Now we can move to.
output circuit के नाम जो
it's not needed this much. Yeah. Now we move to this graph. Yeah. Now I move to this graph. Now I don't know whether you have already observed this graph or not, or have you observed it closely? Never. Now you see. This is called, this is called a semi-log graph paper. You are comfortable with the linear graph paper. This green color graph paper, right? This one is orange color graph paper, and the thing is that it is called semi-log. It's not a linear graph paper. So what is the reason? I have already mentioned. Why should you go for a semi-log graph paper? Because now, although for your case it is not possible to draw the entire circuit, this low frequency, high frequency on a single semi-log, you require two. Why I am coming to that? First of all, you just identify what is the essential property of a logarithm function. What does it do actually? It's the opposite of exponential function, right? For exponential function, if you go from 1 to 2, e to the power 1 to e to the power 2, that difference, and e to the power 2 to e to the power 3, that difference is even larger. Right. So kind of expansion. So that's why this exponential expansion. Exponential means expansion. And log is just the opposite. Compression. Log is the opposite thing. Compression. Now, using a calculator, if you find out this log, so whenever I say log, so remember it's log base 10. Log base 10 always. dB scale, the voltage we have already calculated. That thing basically in the dB scale, what is that? 20 log of that gain will give you the gain in dB. The ratio is basically VO by V in, and if you take like 20 log of that gain, 20 log of this ratio gain, it will give you the dB gain, right? Decibel. So whenever I say log in this class, that is log 10, log base 10. Okay, there is no doubt about it. Disclaimer that log means log base 10. Okay, so what is log of 10? That means if the argument is 10, what is the value? 1. Okay, log of 10 is 1, right? What is log of 20? If you just calculate, you will see that this log of 20 is coming out to 1.3, close to 1.3. Log of 10 is 1, log of 20 is 1.3, right? So 10 to 20. So what is the gap? 10. 10 to 20 gap is 10. The value, the change is on how much? So here the frequencies axis, the change is by 100%, right? But if we consider the log, that is only 30%, 1 to 1.3. Now if we calculate log of 30, that is you will see that value is 1.47. So now you see 10 to 20, that change was 0.3. 20 to 30, the change was 0.17. So same change in argument, right? Same change in x value, but in the y value the change is reduced. That means there is a compression. Log of 30 is 1.4, log of 20 is 1.3, log of 30 is 1.47. If you calculate log of 40, that difference is even less. It's 1.6. So first is 0.3, then is 0.17, then is 0.13. Like this, ultimately log 10, 20, 30, 40, 50, 60. Now if you calculate log of 100, that will give you 2. Can you feel the difference? Log of 10 is 1, log of 20 is 1, the difference is 0.3, log of 30 is 1.47, log of 40 is 1.6, and log of 50 hopefully it is like 1.6 times. Ultimately log of 100 is 2. So if I consider this, this x-axis not as a linear function but as a logarithmic function, then you have to mark the points differently. I'm coming to that. That is a one idea of, that is one concept of your logarithmic expression. Now, whenever in some graphs this nonlinear thing is there, only along this horizontal axis, only along the x-axis. Now you see that there is a peculiar kind of difference. If you just observe over there, this is 1. Okay, I'm coming to that. This is 1, right? This is 1. This is 2, right? Try to understand. This is 1. This is 2. Mark over there. This is 1. This is 2. Okay. This is 3. Linear graph. What should we expect? If this is 1 to 2, 2 to 3, that difference should be same. But log graph 1 to 2. Consider it to if it is 1, let it be 1.3. 2 to 3, even less. 3 to 4, even less. 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9, 9 to 1. Can you get the point? Now just think that suppose this is your 10. This is your 10 hertz. This is 10 hertz. This will be 20 hertz. This will be 30, 40, 50, 60, 70, 80, 90, 100 hertz. Done? If it is 100 hertz, what will be this one? 200 hertz. Right? 300, 400, 500, 600, 700, 800, 900, 1 kilohertz.
2 kilohertz.
Right? 2 kilohertz, 3 kilohertz, 2 kilohertz, 3 kilohertz, 4 kilohertz, 5 kilohertz, 6 kilohertz, 7, 8, 9, 10 kilohertz. Right? 10 kilohertz, 20 kilohertz, 30 kilohertz, 40 kilohertz, 50 kilohertz, 60 kilohertz, 70 kilohertz, 80 kilohertz, 90 kilohertz, 100 kilohertz. 100 kilohertz. 200 kilohertz, 300 kilohertz, 400 kilohertz, 500 kilohertz, 600 kilohertz, 700, 800, 900, 1 megahertz. You started with 10 hertz. You started with 10 hertz and now you have ended at 1 megahertz. But in your case, it is tens of megahertz, hundreds of megahertz, 200s of megahertz. Obviously, you require not a single graph, rather another such graph. One for your input side, another for your output side. Okay. So that peculiar behavior is there along this x-axis. What about the y-axis? What about the y-axis? This difference, this difference, this difference, this difference. Are they different?
No, sir.
They are same. So along x-axis there is a change. Because I would like to observe the change from say tens of hertz to hundreds of megahertz. Right? That is gain. Along y-axis that is gain. So what is maximum gain? What you have got? Like if I just consider the fraction, that is 1.989. What is the minimum value? 0.24. It is possible, no? 0.24 to 0.9. It's possible. That's the linear variation. So this logarithmic variation is there along this x-axis, but along y-axis, this is linear. Okay, I'm coming to that. So that's why this graph is known as a semi-log graph. There is another graph which is known as log-log graph. Both side log. Log-log. But this is semi-log. Why semi-log? Because along this x-axis only log is there, on y-axis there is no log. Now the thing is that in your case, so I've started from this point. So started from this point. If it is 10 hertz, that value was like 1 megahertz. But in your case, you have to go up to 200 megahertz. Possible. At least you can. So how many cycles are there? You just observe. It's called 5 cycles graph. How many cycles? This is 1 cycle, second cycle, third cycle, fourth cycle, 5 cycles. So 5 cycles. There is 3 cycles also. 5 cycle graph. 5 cycles similar graph. But in your case, you require 8 cycles. Now I have searched a lot. Last time while I have given this problem to your seniors, I searched a lot, but I never found this kind of graph paper, at least in Kolkata. Then what I have done, I have just taken a printout. I've taken a printout, and that was basically given to the students. 8 cycles graph paper.
Sir,
it is not available.
4 seat 8 cycles देखले तो मैं देखते ही पाऊँ ना.
No, that should be bigger one. That should be bigger one. Right. So for this case, what is needed? So in order to do that, so you require 2 such graph papers. So I'm just telling you the trick. So now, okay. So suppose so we start with, say, let's start from this point. Or you can start from this point as well. No problem. Okay. So let's assume that. Yeah.
Sir, can't we start directly from 10 kilohertz?
You can't, because we have to identify the change from 10 hertz only. You can't start from 10 kilohertz. You can't start from 10
Sir, in the first one it is from 10 to 10 kilohertz. That we can find.
No. 10 hertz. 10 hertz to 100 hertz. We start from 10.
So that we can easily plot 10 kilohertz. And for the next one we can start from 10.
Okay, I'm explaining. Any doubt in understanding the similar graph paper? No. Okay, now let's start. Suppose this is my 0 point. Suppose this is my 0 point. This is 0. Huh? Then also no problem. This is 0. And then let it be 0.1. Yeah, or let it be say 0.25, 0.5, 0.75, and suppose this is 1. Okay, this is 0. This line is 0. So first one is 10 hertz. At 10 hertz, the value is 0.278. 10 hertz value is 0.278. So this is 0.25. 0.5 is, so what is the difference between if you consider small 0.25 by 10. 0.25 by 10, that is 0.025. Right. So what about your 0.278? Where to place this 0.278? Only one small. So at 10, so I can call, let's take, yeah, so this is 0.2, this is 0.25, this one, and at 10 hertz, if I consider this is my 10 hertz, then let's take a different color. Then at 10 hertz, what is the gain? 0.278. So this is this point. This is 1 point, right? We started from 10 hertz. At 50 hertz, the value is 0.818. Where to play? Where is the 50 hertz? Where is it? This is 10, 20, 30, 40, 50. Yeah. This one? The value is 0.818. 0.818. So 0.818. So this is 0.75. 0.75. Okay, 77, 79, 818. Okay, let's mark this point. This is another point. 50 hertz. Then at 100 hertz, it is 0.94. 100 hertz. So 100 hertz means which one? This one is a 100 hertz, right? What is the value? 0.94. So let it be second. Yeah. So let it be over there. I've got 3 points, 10 Hz, 50 Hz, 100 Hz. You can take more points as well. You can take 20, 40, 60, it doesn't matter. But at least 3 points so that you can draw. You can find out what should be the corresponding variation of the graph. Okay, 100 Hz, 0.94. Then you go to the 1K part only because already it's towards the saturation, right? Now let's take 100 Hz. It is like how much? 0.986. 1K. At 1K it is. So 1K is this one. This is 0.986. 1K. Right? 10 kilohertz. 0.986. Means you are almost towards the. You have entered into the mid band. Okay. 9. So this part is easier part. And 100 kilohertz, okay, 100 kilohertz is 0.989. Okay, you just make it 989. Light slightly more or okay, then 2 decimal point it is this one. Now comes the problem. It's 100 kilohertz. It's 100, right? Now you have to break it because your graph has to be drawn up at least up to 200 megahertz. You have got up to 100 kilohertz only. So this much last point is 1 megahertz. Last value is 1 megahertz, right? So what you can do, you can consider, okay, this frequency is basically, this is basically how much? 100 kilohertz, no?
100 kilohertz. 10 kilohertz.
This is 100 kilohertz.
10 kilohertz.
Is it 10? 10 hertz, 100 hertz, 100 hertz, then 1 kilohertz. 1 kilohertz and 10 kilohertz, 10 kilohertz and 100. This is 100 kilohertz. This is 100 kilohertz. Okay. So now the low frequency operation, the low frequency region. So you require this graph. Using this graph, you can draw this low frequency part. So I've got how many? 1, 2, 3, 4, 5, 6 points. You already got. Now join them. Freehand join. You just join them now, just like this. Done? The low frequency part. Half done. Similarly, the right hand side, you can also do the same thing. You start from 100 kilohertz only. You start from 100 kilohertz. Suppose this is your 100 kilohertz. 100 kilohertz, then 1 megahertz, 10 megahertz, 100 megahertz, and 1000 megahertz. Okay. So, okay, let me just emphasize on the low frequency side. Once this is done, then you have to find out what? You need to find out the bandwidth, the 3 dB bandwidth. 3 dB, 3 decibel bandwidth. So, for this, what you need to do, you just, okay, let me connect, right? Let me connect like this. So, in no talk, you have joined the points, 6 points you have joined. Then you have to find out the lower cutoff frequency. That is FL. FL you have to find out for this high pass filter, lower cutoff frequency. So typically you know that value is given by 1 by twice by tau. But that time you have done it approximate calculation, and this calculation is exact calculation. Right? So had this been 0.989, so now you have to find out where is this 70.7%, 1 by root 2. Just calculate, find out 0.989 multiplied with 0.700. What is that value? Just tell me. 0.989 multiplied with 0.986, but let it be 0.98 only.
0.699.
0.69. 0.7. Let it be 0.7. It should be close to 0.7, right? So now you have to identify where is my 0.7 in this graph. Where is my 0.7? This is 0.75, 0.5, 0.7. Where is my 0.7? You should expect where? I think 2, na? 2 side. Okay. So yeah, using black. Let this be 0.75, 0.75. I think. Suppose about here. Suppose this point. Suppose this point. This point corresponds to what? This point corresponds to 70%, 70.7% maximum. So this point corresponds to FL. Right? Now the trick is the last job is that you have to identify. You understand how to calculate this FL? Yeah. So this is a frequency. This is a frequency that is FL, lower cut-off frequency, corresponding to the high pass filter. And then you have to identify what is that particular frequency. Can you tell me what is that particular frequency? This frequency, how much? No, that is a value. That is a value. I mean the gain value. But what is this frequency?
30 hertz.
Not 30. This is your 30 hertz, right? And then I'm telling you, hopefully cannot see from that distance. After that, you have 1.5, or let it be okay. Let it be 2 or 1.5. So what will be that frequency? No, you can observe. This is 30 hertz. This is 30 hertz, and then this is 40 hertz. It is close to 32. It's 32 hertz. Okay, this is 32 hertz. So therefore, your FL is coming out to be 32 hertz. Right? Approximately 32 hertz from graph itself. Similarly, you have to do the same thing, considering 100 kilohertz to be my this side. Suppose 100 kilohertz is this side. You draw another graph. I mean this low pass response and the high frequency side, and then find out the higher cut-off frequency FH. You find out the difference FH minus FL. That will give you the bandwidth of this amplifier circuit. Bandwidth you have to calculate, not mathematically, but from the graph itself. Yes. That is the entire thing that you have to do. Any doubt? Anybody having any doubt in understanding this similar graph paper? I mean, I have already explained. We are talking that time. It's 70.7%. The gain is 0.98, 9.98. 70% of this how much? 0.7, 0.699. Now had this been 1, this is 0.75. This is 0.75. So this is 0.25, 0.025 is the difference. For small unit, 0.025, right? So you have 0.75 is how much? 0.05. So 2 units drop. This is the point. That is the point. Okay. Any doubt? No doubt. If there is no doubt, then I can simply conclude this lecture right at this point.